Okay, so this is the 15th lecture. In this lecture, we're going to discuss an important generalization of the coin flipping game. So, the coin flipping game was the first place we started to see the power of the so-called calculus of infinitesimals in probability theory, where the long-term behavior of a collection of discrete random events appears to approximate a continuous function that can be integrated and differentiated to obtain information about probabilistic quantities in the large scale limit of discrete events. So, this is a fundamental phenomenon in all aspects of science and engineering and even kind of social studies that deal with a lot of data. It's the fact that if you have enough data points where the definition of enough is kind of a scientist's thing, not a mathematician's thing, but if you have enough data points for whatever purpose you're trying to do, you can pretend that these are not discrete things. They are together kind of a continuous matter that is shaped like the bell curve. And so, that's why the concept of integration comes from like this picture of a histogram with increasingly fine intervals where you have some kind of continuous curve that you think you're trying to calculate the area underneath, and you can think of the typical picture you see with rectangles under a curve for integration as kind of a probabilistic histogram approximating this continuous distribution where the little intervals with these thin rectangles in the integration picture are the representing the fineness with which you examine this population. So as you get more and more rectangles and they get thinner and thinner, you approach the integral of whatever curve you're dealing with, which in probability is usually the bell curve. And you can think of that as just sampling at finer and finer distinctions this numerical variable that you're dealing with. So you have some numerical experiment which is giving you a number according to some random law, and what you want to do is you want to say that this is impossible to predict on a single data point level, but if I repeat it over and over again, then some clear patterns emerge, which, because of math, turn into the bell curve. And so the idea we want to study in this lecture is kind of exactly the right mathematical hypothesis to ensure the emergence of a bell curve as a large scale limit of a histogram for your population with this numerical variable. So, like the usual bell curve is centered at zero, which is maybe not the most natural thing to think of for a lot of physical situations where you see bell curves in media or texts or something, like, it would be a pretty cold place where the temperature average is 0, but we can think about somewhere like that. I don't know. Well, it depends on Fahrenheit or Celsius, but, I'm sure there exists somewhere on Earth where the average temperature is 0 Fahrenheit, and you could think that there's probably a bell curve on either side of that 0 Fahrenheit, which looks like a normal distribution with a certain variance, and maybe its standard is probably not actually variance 1, but you can imagine the temperature having mean 0 and variance 1, and measuring that over and over again and collecting these data points into little histogram buckets, which represent a discrete probability mass function. And then once you have enough data points, you can make the histogram buckets finer and get another probability mass function. And the great insight of what's called the central limit theorem is that this picture approaches a bell curve under certain fairly general mathematical hypotheses. And so the idea in this lecture is, what mathematical hypotheses do you really need to see a bell curve? We saw it in the coin flipping game, but the coin flipping game is just one specific example. The bell curve arises in much greater generality than the coin flipping game. So the mathematical hypotheses you need are independence and identical distribution. Theoretical mathematicians have spent a century fussing with those hypotheses and pushing them toward a more and more relaxed direction, but relaxing the hypotheses of the central limit theorem is not something that we need to worry about. We can just say that there's this amazing thing which happens if you make these two pretty simple assumptions: independence and identical distribution. And so what I'll do in this lecture is try and convince you that these two mathematical hypotheses, once you understand them, are a good way of representing the phenomenon of repeating the same experiment where you have no causal connection between distinct trials. So the essential thing the coin flipping paradigm communicates with what our physical intuitions about coins tell us is that the last flip of the coin has no effect on the next flip of the coin. And that's what will formalize as independence of random variables. And the other hypothesis is that it's the same coin every time. And not only is it the same bias of a coin, but it's the same coin instead of a dice, or the same coin instead of picking cubes from an urn, or instead of changing the probabilistic experiment, you're repeating the same probabilistic experiment over and over again. And so these kinds of situations, repeating the same experiment with no causal connection between trials, are mathematically bound to show you bell curves. They have no choice. It is a law of empirical reality that if what you're studying accurately conforms to these hypotheses, it will distribute itself like a bell curve. And these hypotheses are so commonly satisfied in physical situations that huge proportions of academia simply think they're tautological. Like in social science and in economics, these hypotheses are basically assumed universally without comment or explicit acknowledgement. It's just, it has to be a very hard science before you collect enough data and see enough detail that you really get the wrong picture from these hypotheses. Like, in particular, it's just a basic assumption in sciences that count people to assume that properties of random people called based on random phone numbers are independent. That's like just something that is not tautological, but it goes as if tautological in not just academia, but polling that dictates gigantic amounts of political contributions and marketing research and everything. Just the idea that, if I have a mathematical uniform distribution on phone numbers or whatever other numbers I'm using to count people, and I pick random numbers, those people will have properties with no causal relation that reflect the general distribution of humanity's properties varying around a random law. But, these kinds of hypotheses are often satisfied in hard science too. It's every physicist's first assumption to think that things have these properties, and if you're wrong, reality will show that to you. But in physics, you always want to start, if you have some random variables, by seeing whether it's consistent that they're independent and identically distributed. And because the phrase independent and identically distributed is so common, it's just abbreviated IIDs. So this concept of independent, identically distributed random variables, people just call an IID process. And it's supposed to formalize mathematically repeated trials of the same experiment with no causal connection between distinct trials. Okay, so here is a mathematical definition which illustrates the elegance of conditional distribution functions. So these definitions are pretty easy to remember because they're short and have brief descriptions in language. And the price of that is they involve the conditional distribution function, which is kind of the most abstract way of thinking about a random variable. But this is something that's often done in math to put difficulty in definitions rather than later on. And so once you've defined the conditional distribution function, it becomes very easy to give a common definition for both discrete and continuous random variables of what independence means and what identical distribution means. So identical distribution means that every pair in your sequence has the same conditional distribution function. And independence means that the joint conditional distribution function of, I used the wrong notation here. I will fix it. Okay, so anyways, the point about independence from this elegant conditional distribution function perspective is that it just says the joint conditional distribution function is the product of the individual conditional distribution functions. So you have this, sorry, I think I've been saying conditional distribution function. I should be saying cumulative distribution function. So you have this cumulative distribution function, which tells you the joint probabilities for all of the random variables satisfying a sequence of upper bounds. And that probability is equal to the product of each individual random variable satisfying that same upper bound. So these are definitions which I've chosen to illustrate the concept of putting difficulty in, or these conditions I've stated to illustrate the concept of putting difficulty in definitions rather than later on in the theory, and so they're very short and easy to remember, but they involve cumulative distribution functions. And so now we're going to interpret them in terms of probability mass functions and which probability density functions, which are kind of more concrete ways of thinking about sequences of random variables than joint cumulative distribution functions. Okay, so we have these two hypotheses. The first hypothesis is identical distribution, and the second hypothesis is independence. So what we're going to do is we're going to think a little bit about identical distribution, and we are not going to assume independence in conjunction with it for this initial analysis. And then later on, we're going to think about independence without also assuming identical distribution. And then at the end of the lecture, we will think about the conjunction of these properties. So let's see some initial facts about identical distribution. So if you have some discrete random variables, identical distribution implies that they have the same set of values and the same probability mass function. So what we can say is that identical distribution means all the information is the same if you look at one trial as opposed to another trial. The setup for the experiment is the same, and you've tried to make everything else constant except for this parameter you're choosing to measure over and over again. So identical distribution represents the idea that your experimental apparatus is trying to isolate this particular numerical parameter, and it's the only thing that's changing about the experimental setup when you go through your various timestamps. So I just want to go back for a second to our definition of IID and note that I started counting from 0, which is a convention that I had explicitly rejected earlier in the course when I said we would start counting from 1. The reason it's natural to start counting an IID sequence from 0 is because it's natural to start with a 0 timestamp at the start of your experiment. So usually the basic thing you have when measuring a varying quantity in experiment is you record a data point at constant time intervals, and you usually just put 0 as the start because you think that 0 seconds have elapsed. So the indexing on IID sequences is very, very closely tied to time elapsed between observations, and that's why we start from 0 time elapsed. So the idea for discrete random variables is that if you pick any two non-negative integers, then those pair of random variables at the two different times have the same values and the same probability mass function. So the random law that you're trying to discover is the same every time you sample a number according to that random law. And for continuous random variables, we've had this consistent analogy that instead of probability mass functions, you have probability density functions. And so what we can say is that identical distribution for continuous random variables constitutes a hypothesis that each one individually has the same probability density function as the others. And just to emphasize, what I'm saying doesn't uniquely determine this object. Saying that the individual random variables have the same probability density function is far from sufficient information to determine the entire characteristics of a sequence of random variables. So the reason is that joint probability density functions or joint probability mass functions in general contain a lot more information than simply the two distinct probability mass functions for the individual random variables. And you can see that here because we're saying that the individual probability mass function is actually not changing at all. And what I need to do beyond this is to assume independence in order to observe the central limit theorem. So it's saying even though I'm assuming that these are all have the same probability density function, that in itself does not determine the joint probability density well enough to conclude the central limit theorem. But it does give you a lot of good information knowing that you're sampling the same experiment over and over again. The reason this hypothesis does not completely determine the random law of the experiment is because there could be correlations or causal effects between distinct time samples, and that's what independence rules out. But identical distributions is that it's sampling from the same probability mass or same probability density every time. Okay, so we can have a look at this example where we have a sequence of random variables which are assumed to be identically distributed but not assumed to be independent. So in this example, we are studying the concept of identical distribution without conjoining it with independence, as we will later. And what we're asked to do is to calculate the difference between the expectations of a pair of these IID random variables where I hope 23 and 9 suggest nothing special about that pair, you know? You can find 23 chromosomes and you can find 9 whatever you want, but those are just kind of supposed to be random. So the idea is that instead of putting variables j and k, I've tried to make it a little bit more concrete and put specific numbers in order to motivate the idea that this difference is always 0 no matter what numbers you choose. So let's have a look at what happens when you calculate the expectation of x23 minus the expectation of x9. So we have a formula in the discrete case which tells us to sum over all values of x23 of the value times the probability mass function. And we're supposed to subtract the same formula with x9 instead of x23. And the point is that identical distribution tells you actually these things are both the same as the corresponding expectations for x0 or for x1 or whatever you want. It doesn't matter if you subtract the same thing from itself, it's 0. And the reason that happens is because we explicitly assumed that all of these probability mass functions were the same and all the value sets were the same. That's what identical distribution means. And we can see another manifestation of the same concept in the case of a continuous random variable a little bit lower down on the screen. So in the case of a continuous random variable, you have even a little bit of an easier task because you don't have to worry about figuring out what the value sets are. For discrete random variables, it gets a little confusing unless you explicitly hypothesize as part of identical distribution that the value sets are the same. But for identical distribution of continuous random variables, because of the nature of probability density functions, that they can be integrated over arbitrary real number intervals, we can just say that these probability density functions are the same. They're all the same as x0, or they're all the same as x1, or that's what identical distribution means. It just means that you get the same number when you calculate stuff with the probability density functions for two different timestamps. Okay, and so let's try and think a little bit about what the consequences of this are. So what the intuitive consequence is that identical distribution means that you're going to have a consistent parameter that you can use as the center for your statistical analysis. So if you don't assume identical distribution, it's really hard to do statistical analysis because the expectation keeps jumping all over the place and you aren't sure what to expect, let alone how to give confidence intervals around the expected number. But identical distribution gets rid of that obvious problem with statistical analysis. You know, a very clear obstruction to statistical analysis would be an expectation that just follows some crazy pattern, like that game where a magical horse was trying to get $100 billion from Jeff Bezos. So, you know, if you don't assume identical distribution, sometimes the expectation can totally defy your attempts at centering a prediction. But identical distribution tells you, okay, I know what to expect in every single case. It's the same. It's usually, to make things concrete, I say what I expect at an arbitrary time is exactly what I expected at the beginning. So that's why I've chosen to switch these sums and integrals to 0 rather than 23 and 9, because I'm trying to make the point that if all you're looking at is distinct timestamps and you're asking what should I expect at 23 seconds, it's the same as what you should expect at 9 seconds, and it's the same as what you should expect at 0 seconds. You're expecting the same number every time, and you're trying to study how it may or may not deviate from that thing you expect, which you already knew at the beginning. Okay, so So now we want to think a little bit about the concept of independence without conjoining it with identical distribution, as we will do later. Okay, so we already had the word independence involved in our discussion when we were talking about events. We had a definition for independent events. And the definition for independent random variables is just mathematically bootstrapping that. It's saying that we're going to call random variables independent if their outcomes are independent no matter what choice of outcomes you pick. So in the discrete case, I have a potential value v for xj and a potential value w for xk. And I'm asking what's the probability that these two random variables simultaneously satisfy this pair of values. And independence tells me that I can calculate that probability by taking the product of the individual probabilities that these random variables are equal to these values. So independence with events let you turn a conjunction into a product. And it's the same thing for random variables. The conjunction of random variable outcomes is the product of the distinct probabilities. And we can rewrite that in terms of the probability mass function as just saying the joint probability mass function is the product of these two individual probability mass functions. So we have the probability mass function for xj and xk, and it should be equal to the product of the individual probability mass functions for the two random variables thought of as objects in their own right. So this is a subtle thing, and it has to do with quantum entanglement, but it's not at all necessary that your product of probability densities is a good approximation to the joint density. That's the hypothesis of independence, and it is supposed to convey the absence of causal effects between different timestamps. And the point about quantum entanglement is you have causal effects where you don't necessarily expect them if your view of reality is excessively localized. But we can say that for probability mass functions, it just splits for each pair of values. And then for probability density functions for continuous random variables, we can say that the events you get from taking a pair of lower bounds and a pair of upper bounds, if you take the conjunction of those, they're independent events in the sense we had from before we introduced random variables. So, random variables are a higher level construct that you can introduce, but you don't have to. You can just talk about events all day if you want to talk about events, and you don't need to know that random variables exist, which is the reason it's logically rigorous to define independence of random variables in terms of independent events, because the definition of an event is more basic than the definition of independence for random variables. So this is, instead of trying to convey the idea that two things that could happen have no causal relationship, like two events, the temperature yesterday and the temperature today, we're thinking them as two numbers that have no causal connections. So, I don't know, but math is largely about numbers, and we have this way of taking the idea of events defined by properties with no arithmetic structure and turning them into events defined by conditions on random variables which do have arithmetic structure. And we can see that here, where we're looking at conjunctions and putting this condition of independence, which allows us to factor joint densities and joint mass functions as products of individual ones. Okay, so let's say we have this sequence of random variables which are assumed to be independent but not assumed to be identically distributed at the moment. So what we want to observe is a certain consequence of independence that is not, or that has nothing to do with identical distribution. And the idea is, again, in order to try and make things a little more concrete, I've tried to pick two numbers seemingly with no special properties in this context, 14 and 3. The idea is that you can pick any two numbers and this always comes out to be 0. So we can see what we have here for these discrete random variables, where we're taking a sum and we have, let's think of the sum that's immediately below the bar after the question ends. So it has two lines. There's a sum over values of x14, and it's multiplied by a sum over values of x3. And so if you recall the definition of expectation for single random variables, this is how we define expectation for single random variables. And then you have a third random variable, which is the product, and it can take on pairs of values, which are the product of v and w. That's what a product of random variables is. It's a random variable that takes the product of values with the joint density. And so the sum initially in the middle of the page has a product of these two things over values of x14 and values of x3. And the line below it with the minus sign has a sum over values of both random variables. But if I did not assume independence, I would not be able to disentangle this joint probability density function in order to conclude that the sum vanishes. It's wildly false that this sum vanishes for arbitrary sequences of random variables that are not assumed to be independent. And what you need in order to conclude that the first thing is equal to the second thing and it all cancels out is you need to be able to do exactly what independence is designed to help you do. which is to split up the joint density into the product of the two individual densities. And so once you've been able to do that, you can say that this is just a very elaborate version of saying that I'm expanding a product. So I have this product where I'm summing over values of x14, and in the other factor of the product, I am summing over values of x3. And I'm multiplying those two sums. And what happens when you multiply two sums? Well, you get a double sum over all pairs of indexes where the first index is from the first factor in your product and the second index is from the second factor in your product. So that's why the values of V and W of x14, x3 are appearing at the very bottom of the page. And so you can see we do indeed have the same thing subtracted from itself, because at the very bottom of the page there's a expanded product, and at the third line in the solution right above it there's a non-expanded product, and they're the same, so the difference is 0. And as I said, I chose 14 and 3 to make things a little more concrete and avoid too much notation, but the point is you pick any two numbers and this comes out to be the way it is. So that's kind of showing you why independence is such a useful hypothesis. It allows you to understand the joint density just by understanding the individual densities and doing a thing we call multiplication, which we like to think we understand pretty well. Okay, so the whole story I've been telling about all this stuff with identical distribution and independence is designed to produce the results which you can see highlighted in teal. So I'm again looking at the long-term behavior of my experiment. So back in the situation I was using to study the coin flipping game, where I'm looking at long sums of my random variable, except now we have the same mathematics we understood for the coin flipping game with hypotheses that are vastly more general in physical interpretation, where you can say this is any experiment that I'm repeating over and over again with the same setup, and there's no causal relation between the different trials. And if you have those assumptions, you can call it an IID process. Everybody, there are a lot more people in the world who understand the little quasi-word IID than there are people who know it actually expands to independent and identically distributed. It's like DNA or something, it's like vast majority of people know what DNA is, but many fewer people know what it's supposed to expand to. And a huge number of people know what IID is without necessarily knowing what it's supposed to expand to, which gives you an indication of how common this hypothesis is in subjects where people really don't want to be dealing with math at all. And the first thing that you want to know about IID processes is that the expectation for the long-term result is just multiplying what you expected at the beginning by the number of times you tried. So another way you could rewrite this would be to divide both sides by n and move the n inside the expectation because it's just a scalar rather than a random variable, and find that the expectation of the average is equal to the expectation of time zero. So the reason I've written it like this is because it's clear how it follows from what we had over here. So over here, I said that x23 minus expectation of x23 minus expectation of x9 was 0. And that was just supposed to be a concrete way of helping you realize that identical distribution means the expectation is always the same. So because expectation of a sum is a sum of expectations, and I'm summing the same number over and over again, I just get n times whatever I expected at the beginning. So you can say that the expectation of the average is what you expected at the beginning. That's a consequence of identical distribution. And the second thing here is a consequence of identical distribution together with independence. It tells you that the variance of the sum is again just n times whatever you expected for the variance from the mean at the beginning. But one of the big themes in probability is that variance is conceptually simpler, maybe, but standard deviations are actually the right thing to look at. The biggest reason is probably because they scale homogeneously with the quantity rather than scaling like the square as variance does. But the thing you want to remember is highlighted in teal that the long-term standard deviation of IID is standard deviation at time 0 times the square root of how many you counted. So it's like the standard deviation grows exactly like the square root function with a constant that's whatever your standard deviation was at the beginning. And the mean grows exactly like the function f of n equals n with a constant that's whatever you expected at the beginning. And so it's like, well, how does my expectation grow? It grows as a linear function of my number of data points where the scale or the slope of the line is whatever I expected at the beginning. So, hopefully that makes sense. If something is the same experiment over and over again, you're just accumulating more and more data. You should expect roughly for the sum of your data to grow linearly with whatever the individual expectation is. And another way of that is saying the expectation of the average is what you expected at the beginning. And then you should expect the deviation around the average to grow like the square root with whatever your initial expected standard deviation was at the beginning. And so obviously the most important thing is that if n is really big, the square root of n is way smaller than n. So the hypothesis of independence and identical distribution gives you really good information because the expectation is much larger than the deviation in terms of the rate at which it grows. And so if you want to look at the expectation and normalize so that you're taking an average, then because you've normalized by n and the deviation was only growing like the square root of n, you will observe concentration around the average, which is the essence of prediction, is to say that, well, my prediction is n times mu of x0, and my confidence interval is square root n times sigma x0. And if n is gigantic, the prediction is way larger than the confidence interval. If mu x0 is 0, that's not quite true, but that's a technicality rather than a serious issue with the concept. And we can just compare this as what we already computed for the coin flip. So I'll stop the lecture there.